Hi, I'm Tamara Broderick. Today I'll be talking about how cross-validation is the gold standard for machine learning evaluation, but it's often too slow in practice, especially for modern complex models. We and other groups have worked out approximations to cross-validation in the past, but all these existing methods work only when data is independent. So here, we develop approximate cross-validation for these really popular models with non-trivial dependency structure. Before going on, I want to highlight that one of the co-first authors of this work is my fantastic student, William Stevenson, who is at this workshop today. I'll highlight the rest of my great students and postdocs on our work at the end. Okay, so the story of some years now in machine learning is that better computation allows us to run increasingly complex data analyses. Again, we can have these non-trivial dependency structures, time series models, spatiotemporal models, models in natural language processing and vision, models in genomics, and so on. In all of these cases, we really want to make sure our methods work, so we need to be careful in evaluating them. Cross-validation is the gold standard for evaluation in machine learning. It's more accurate than alternatives, it's easy to use, you just rerun your data analysis multiple times, but that also means it can be expensive. When you're already pushing your computational limits, especially with one of these complex models, running your analysis multiple times can be prohibitive. So in past work, we and other groups have developed approximations to cross-validation. We've demonstrated that they're fast and accurate in both theory and practice, but all of this existing work assumes that data are independent and that we can fit models exactly. In these complex structured models, neither is really true. The data are definitely not independent by construction, and typically it would be too computationally costly to run all the way to machine precision. So for instance, a practitioner will run something like stochastic gradient descent for some number of epochs and then stop when it's looking good enough. So our contribution then is to develop approximate cross-validation for these structured models used so widely in machine learning. To make this really practical, we also extend approximate cross-validation to take an imperfect model fit. In this case, we show error grows smoothly as the noise in this fit increases. Okay, so first, let's look at the setup. For existing approximate cross-validation methods. We start with a data analysis where we're interested in learning about some parameters, let's call them theta. We assume that we have data points indexed by n, and for each data point, we have some loss associated with it. Let's call that fn. This could be a negative log likelihood. So we'll find the total loss across all of the data points by taking a sum. And we might estimate the parameter theta by minimizing the loss, or equivalently the average loss. So we'll get out our estimator, let's call it theta hat. And sometimes we'll have a regularizer R. This could be something like a log prior, or a negative log prior. Okay, so that's our data analysis, and we can think of cross-validation as just reweighting the data points in this analysis. So we can have a weight Wn for the nth data point. So we're just adding in this weight Wn here. And so the original analysis sets all the Wn to be equal to 1. And for instance, if we were interested in leave one out cross-validation, we would take each Wn to 0 in turn in each fold. And you can have other types of cross-validation or even the bootstrap in this framework, but a key thing to note here is now each theta hat is really a function of the W. Okay, so now there are a few types of approximate cross-validation that we could try, but some of these require an expensive matrix inversion for each cross-validation fold. So we're going to focus on what's known as the infinitesimal jackknife, or IJ, because it avoids this expense. Now the idea here is that we expect theta hat doesn't change too much for different folds because W is not changing too much. So we can do a Taylor expansion in W for each fold, and we're going to come up with our approximation. Let's call it theta hat IJ, and that'll be an approximation of the exact theta hat. Now the key to our approximation is that we only have to run the original data analysis once to get theta hat at the all ones vector, and then we just plug that in to get our estimate at all of the other vectors of W. We can calculate our approximation across all the folds without running any more optimizations, which we're imagining is pretty costly here. And running our analysis once is sort of a fixed cost. I mean, you have to run your analysis once to do anything. Now we can't get away from that, but we also have to calculate these Hessian and gradient terms, but we can do that pretty easily with autodiff tools. And so once we have all of these quantities, we can compute our approximation across all the folds using the formula here. Okay, so that's the IJ. But the first problem here is this loss summation. If these are all negative log likelihoods, summing the negative log likelihoods is equivalent to having a product of likelihoods. That is to say, we're making an independence assumption by even setting things up this way. And there are tons of models that we commonly use in machine learning that just don't satisfy this assumption. Moreover, the Taylor series expansion here assumes we have access to this exact fit theta hat at the all ones vector. But in practice, for these complex models, we really just run some epochs of our optimization procedure, and we're usually pretty far from machine precision at the end of that, because it would just cost way too much to keep going. Okay, so here what we're gonna do is we're gonna extend this approximation framework, this IJ approximation framework, to structured models that don't assume independence. We develop algorithms that are easy to use and automatic with autodiff tools. Next, let's let theta super S be whatever we actually get in practice from running our optimization procedure for S steps. So we're here going to extend approximate cross-validation to take this input rather than the perfect optimization, and we show that error decays gracefully away from this perfect fit. We also show our method works on a wide variety of experiments. I'll show just a couple due to our time constraints today. So first, let's look at a traffic monitoring and event detection task. So here data was collected on a freeway in LA, and we consider a time-varying Poisson process model. In each of our accuracy plots, we're going to consider CV folds, cross-validation folds, removing some percent of the data. Here it's 2%. Each fold removes 2% of the data. Each point can be removed uniformly at random, or the points can be removed in contiguous chunks. So we're going to actually consider both cases. So here we have the IID point removal, and here we have the sort of block or contiguous chunk removal. Now we're going to test the accuracy of our algorithm at recovering theta hat in every fold in CV. So there's a red dot here for every fold. The exact theta hat is on the horizontal axis. Our approximation is on the vertical axis. So this is much stronger what we're requiring in terms of accuracy than just averaging over all of the folds. Okay, we can also look at 5% of the data held out and 10% held out. And we see that for all percentages of the data held out here, all the red points are basically on the x equals y line, which is to say our approximation is very accurate. Now remember, the whole point here is that we want a big timing speed up, and that's in fact what we see. We're looking here at a timing plot in hours across different size subsets of the data. Those are on the horizontal axis. Note that the vertical is growing on a log scale, so we have a speed up of at least a factor of 1,000 here. In fact, we provide a big O analysis that suggests we'll see even bigger speedups and even bigger data sets. We're really just constrained here by the running time of exact cross-validation. Okay, so we also look at a task in named entity recognition with a bidirectional LSTM conditional random field, or CRF. We emulate a task like transfer learning, and we're again plotting for each fold the exact theta hat on the horizontal axis and our approximation on the vertical axis. But here, this is our approximation with an imperfect optimization. The first plot we see is after only 25 epochs of SGD, so we're left with a high grad norm. That's what you're seeing in the text in the plot. Even after 85 epochs, you can see the grad norm is still clearly non-zero. So we're really not at sort of, this machine precision optimization. But we know that we see the points are getting closer to the x equals y line as we run for more epochs as expected. And even though the grad norm is far from zero after 85 epochs, our approximation is still spot on. And it's not that bad at 25 either. I'll encourage you to check out our paper for more experiments. Here's the information. It should be up on the archive soon. In fact, it might even already be up by the time we're actually all meeting together. In the meantime, you can check out our previous papers in approximate cross-validation. These lay important groundwork in the case of independent data that I discussed earlier. But here we go beyond that, and we develop approximate cross-validation for models with interesting and complex and modern and helpful dependence structure. We extend approximate cross-validation to allow imperfect model fits. And we check this all works in theory and practice. Our method provides many orders of magnitude speedups and is still really accurate. Thank you.